Well, it's that time. Exam 2. And all of chapter 3 was just out about integration techniques, right? Before we only just had use substitution, which was just the chain rule, right? But now we have ways to integrate products. Okay, integration by parts is just a product rule in reverse. We get the trigonometric family of integrals by trig substitutions and clever use subs that way. We know how to do partial fractions for rational functions, and we now know how to handle improper integrals. So the review section, okay, just like the last one, okay, it's going to be split into multiple parts. This one here I'm planning for 4. And in the first part, I'm just going to talk about integration by parts. Now, this assumes that you've already watched the corresponding videos on each section. Okay, so I will be going a little bit faster, just like in exam 1 review. So if you ever need to review a technique, please go back and watch those videos and go back and refer to your notes, the textbook, and any other reference that you like. So let's just get into it. So we have an integral here, x squared e to the minus 3x, and you might be looking at that, it's like, what do I do? How do I know what technique to use? And the way I see this, okay, I have a product of two functions, okay? They're kind of different. I don't have a derivative of one embedded in the integrand. And so I'm just going to go ahead and use integration by parts here. Now, this one is actually right for the table. Okay, this is right for tabular integration. Okay, so I'm going to go ahead and set up my DI table here. And remember that the D column is your U's, and your I column is your DV's. And so, what do we make choices of? Well, let's remember the Liotte heuristic. Okay, let's do it in this color. The IBP heuristic is Liotte. Okay, let's remind ourselves of that real quick. Log, inverse functions, algebraic functions, trig functions, and exponential functions. Okay? And then, of course, if you look from the top down, that's how you select your, well, what do you mean? Do you remember? That's how you select your DV. Sorry, that's how you select your U. It's been late. I'm tired. Okay, and if we look from the top, from the bottom up, that's how we select our DV. And some people remember this as detail, okay, for selecting your DV. So what do we pick here? Well, let's set U equal to x squared, and DV is equal to the rest. Okay. And now remember in the table method, the DI method, what we're going to do is we're going to go ahead and differentiate in the D column until the thing vanishes, until the derivative is 0. Okay, so if we do that, we know our power rule just gets applied a bunch of times here, right? And then we're going to integrate as many times as I differentiate it, okay? So you should have the same number of rows. Now, remember that when I integrate an exponential function, I get the same thing back, but I have to divide by the slope, okay? But if I have e to the kx, the derivative, remember, is k e to the kx, and the integral is 1 over k times e to the kx. Let's just write that down here for completeness sake. Okay. Remember, if you need to refresh yourself on your basic derivatives and integrals, please refer back to your tables. Okay. So we fill in the tables here, and of course we get minus sign, okay, because we have a -3 in the exponent here every time. So here we are. And now it's just as easy as, well, as it said in standard deliver. Well, we have plus, minus, okay? Tic-tac-toe, okay? So remember, for the table method, okay, we join the first thing in the D column to the second thing in the I column and repeat, okay, with the alternating checkerboard pattern. And each of those red shoelaces is a product, okay, associated with the sign here, okay, associated with the signs that appear there in the light blue column, okay? So let's erase those for the moment, okay? And what do we have here? Well, we just read it off here. Minus 1/3 x squared e to the minus 3x, okay? Then minus 2x over 9 e to the minus 3x minus 2 over 27 e to the minus 3x plus a constant. And folks, that's it. This is why the table method is so powerful when you integrate a polynomial against a sine, cosine, or an exponential. Now, of course, you can also do this classically with the UDV formulation, okay, the integration by parts formula. Remember that the table method is not a shortcut, it is a shorthand. Okay, so the table method, the DI method, kills this problem immediately. Okay. Now, let's move on to our next one. X to the fourth log x. Again, how do I approach this? I see a product of two functions. They're kind of different. I'll see the derivative of one embedded in the other. So parts again. Let's just try parts again. And this isn't ripe for the table method because, well, I don't have a polynomial against a sine, cosine, or exponential. Okay, I do have a polynomial here, but is that what the Liotte heuristic tells me to choose as my u? No. Remember, the Liotte heuristic, okay, says that u should be the log here, okay? If it appears at the top of the hierarchy, that should be your u. So we're just going to go ahead and use the classical formulation here, okay? U equals log x. dv equals x to the fourth dx, okay? And you can just go ahead and fill in the table here. Okay, du is 1 over x dx. That's the derivative of log x. V is equal to 1/5 x to the fifth. That's the integral of x to the fourth, just power rule. Okay, and remember, okay, that IBP, the integration by parts formula, is the following. The integral of u dv is equal to uv minus the integral of minus the integral of v du. Okay, that's our classical formulation. Okay, that's the classical formulation of integration by parts. We should still know this formula. It's just a product rule in reverse. And of course, if you have a definite integral, you just evaluate on the boundary. Okay, you just do the boundary evaluations. Okay, so let's write that in for completeness here, shall we? Okay, just as a nice refresher. Okay, there we go. And so now we just follow our path, right? So let's just write down what we have here. The integral of x to the fourth log x dx by using your choices above there, okay? uv, so 1/5 x to the fifth log x, minus the integral of v du. Let's write it out in full here. So 1/5 x to the fifth times 1 over x dx. And take a look, right? X to the fifth divided by x gives me an x to the fourth, okay? So let's write down that next step here. So we have minus the integral of 1/5 x to the fourth dx. And yes, you can pull the 1/5 out of that integral, but you don't really have to, okay? Power rule, okay? First part stays the same here. The second thing, we have x to the fifth, okay? Oops, let's put that here. But then I divide by 5. 5 times 5 is 25. So I have a 1 over 25 x to the fifth plus a constant, and that one's done. Okay, we saw an integral like this, okay, in the original integration by parts video, okay? So please, if you need a refresher on how to handle these classes of integrals and how to recognize them, go back and watch those, okay? Let's look at our last parts integral here, okay? I told you this was going to go fast here. That's not parts, Sean. Actually, it is. Because remember, lurking behind the scenes here, okay, is an invisible 1. How does that help me, Sean? So remember the Liotte heuristic? Okay, I'll just write it down here, okay? Remember the Liotte heuristic? Inverse function, algebraic function, trig function, exponential function. What type of function is arctan? It's a trig function, Sean. Well, yeah, but it's actually a little stronger. Remember that arctan is actually tangent inverse, the inverse tangent, okay? Not 1 over tangent, but the inverse tangent. That's going to be your choice of u here, okay? That's an easy thing to take derivative of, okay? So we're going to build our table here. U is equal to arctan x. dv is equal to, let's move this real quick here. Okay. dv is equal to the rest, 1 dx. Okay, we saw this when we integrated the natural logarithm. Okay. Now complete the table. du is equal to, well, the derivative of arctan is 1 over 1 plus x squared dx, and I'll just go ahead and write it like this. Same thing. Okay. And then v is equal to x. And as always, folks, follow the path to success. So we use the integration by parts formula, so let's go ahead and write down what we have. The integral of arctan x dx is equal to u times v, so x arctan x. Okay, let's just keep that there. Okay. By the way, for you folks that know your programming languages, okay, arctan is written atan in a lot of languages like C and Python. Okay. Now we have v du, so x over 1 plus x squared dx. But how do we tackle that second integral? Okay, this is where we have to remember our techniques, okay? We don't use just one technique. You may have to use multiple, okay, in tandem, okay? Well, I see a function, and I see its derivative, okay? This is a clue that I should be making a variable substitution, okay? Now, I've already used the letter U here, okay? I've already used U, and I've used V, so I'm going to use the next letter of the alphabet, W. Doesn't really matter what you change variables to, but check it out. If I let W equal 1 plus x squared, then dw is 2x dx, okay? But notice here that my integrand, okay, the integrand only contains x dx, so I'm going to divide by 2, right? Remember U substitution? So 1/2 dw is equal to x dx. Now, you could also do the trig substitution here, say x equals tangent theta, okay? You'll get the same thing. I honestly found the U substitution a little more natural here, okay? When you have denominator and the numerator, okay, of this fraction is degree 1 less than the denominator. So with all that aside, okay, what do we have here? Okay, and if you already spot the antiderivative, you just go ahead and jump to that step. That's fine. Okay, but this is just illustrating how we use those techniques here. So x dx is 1/2 dw, so I'll write that as 1/2 times dw over, well, 1 plus x squared is now w. How do I integrate 1 over w? That's the logarithm. So x arctan x minus 1/2, let's fix that, natural log of absolute w plus a constant. And now we just go ahead and replace back, okay? So the results here. X arctan x minus 1/2 log of 1 plus x squared in absolute value plus a constant. And folks, you're done. You see how neat integration by parts can be? It's powerful. The granddaddy technique, okay? This is the one that's really powerful and used a lot. Okay, now a quick remark here. You technically don't need the absolute values here on the 1 plus x squared since it's always positive, but to keep kosher, you should just put them down, okay? All right, so we've gone ahead and reviewed some nice integrals that we had to use parts for. Now, of course, if you had a definite integral, yeah, just the same thing, right? Just evaluate on the boundary and do whatever, right? The game doesn't change, okay? So that's integration by parts out of the way. All right, in part 2 of the review, we're going to go ahead and tackle all the trigonometric integral families at once. And I'll see you in the next one.